Good morning. This week, lab, we are looking at impedance. So we've been looking at AC circuits, and we realize that we have, in AC circuits, resistance does not only come from the resistors. We have to be thinking in terms of the resistors and any capacitors and any inductors. They all can provide what effectively is resistance. And the combination of all those different types of resistances are referred to as impedance. Now, in the lab today, what we want to be able to do is we want to be able to take a couple of solenoids. You may have seen these before, maybe you've seen them, maybe you haven't. They've shown up in some other labs, I think. But we've got a couple of solenoids. We've got the really, really big solenoid with the 3,250 loops. And then we got the smaller solenoid with the 540 loops. And what we want to be able to figure out for these is how much resistance is there in each of these if I'm powering it with a DC power supply. So that's easy enough, right? We set up a DC power supply, we find out how much resistance there is in a solenoid. Now, if we switch over to AC, that complicates things. If we operate this with an AC power supply, then in addition to the resistance, we have what we call inductive reactance. And so these are the impedance diagrams that we've been looking at in class. And we said that the way this gets combined, in some sense, the resistance, because it's oscillating current, the resistance is out of phase with the reactance in the inductor. So these are both, each of these solenoids, in addition to being a resistor, they're an inductor. They have both properties to them. So I've got to treat those as a combination of both. And so for a solenoid, it's going to have some resistance, it's going to have some reactance, and the combination of those, using Pythagoras' theorem, will tell me how much impedance, how much overall resistance, how much overall impedance does that device have. Now, so what we're going to do is this. We're going to get our power supply set up, which may look familiar too. Here's our power supply. We've got DC power on here, and we have AC power. So I can switch back and forth. Right now it's turned off. There's the DC. I can turn that up, and that will put us at what it states on here is 5 volts of DC. And then what I can do is I can take those very same wires and switch over and move it to 6.3 volts AC. Ooh, I gotta get one of these inductors back again. Let's see. The circuit's incomplete. So what we've got this time is there's the solenoid. So here's the power supply, and as we've pointed out, I can switch from AC to DC. Here is the solenoid. The solenoid has not just an inductance, but it has a resistance also. And then here is a new gadget. This is a resistor box. And so what I've got here, let me show you what this looks like. So here's a resistor box. These are really handy. What they have is I can just dial in a certain amount of resistance. So it has 1s and 10s and 100s. And if I open it up, there's a bunch of resistances inside. And so I can dial in 1 ohm or 2 or 3. I can dial in 10 or 20 or 30. I can dial in 100, 200, 300, 400, 500. So everything goes 1 through 9. I could dial in 575 ohms. So however many ohms I want. I mean, there's a limit here. This device goes up to 1,000. It goes as low as 1. So what I can do is I can just vary that however I want. They are advertised to be precision, and we've done pretty well with our resistor boxes over the years. So they do seem to, at least we end up with quite consistent results working with them. So here's the resistor box, and here's the solenoid. Now, in today's lab, we're just going to work with a voltmeter. So rather than try and keep track of voltage and current going through these circuits, as we've mentioned before in labs, voltmeters are more, when I have my multimeter set to a voltmeter, it's more durable. It's harder to burn out a voltmeter than it is an ammeter. If I have it set to ammeter, I have to be more careful with it. And then also, the way we're going to be measuring these voltages is we're just going to be using ratios. It turns out that if I set up this circuit that has a power supply, a solenoid, and a resistor box, and then I measure the voltage across the solenoid, and I measure the voltage across the resistor box, I'm calling this V0 and this V, that the ratio of V to V0 equals the ratio of their resistances. That's it. They both have the same current going through them, and so a ratio of voltages is equal to the ratio of resistances, and that gives us an easy way to go in and measure resistance without having to use an ammeter. I can just use a voltmeter, and I've got the voltmeter in quick mode, and so what I can do is, let me turn this on. I guess I gotta dial this down. I've kind of overdone it here. I'll dial this back. Maybe I'll do 1 or 2 ohms. Maybe I'll try 2. So here's 2 ohms here. And then what I'm going to do is, I'm going to turn this on. And this is reading 3 oh, it's jumping around. Okay, this has got to settle down. I wonder if it needs a new battery. Boy, it really is. I'm going to have to get something and lock it into place better than this. So what I can do is I can measure voltage here, and then I can measure voltages here. And I can take the ratios of those. And so, yeah, I think, let me try that one more time. All right. It's usually pretty stable. But what I can do then is I can measure those 2 voltages. Oh, you know what I've got? Let me move back to DC. It should work AC or DC, but let me move back to DC and try this too. Because I think I've got the voltmeter set to DC. All right, there we go. So this is, let's see what we have here. Let me turn up the voltage here just a bit. Okay, so the voltages are showing up, and what we can do is we can solve for the resistance in the solenoid by taking R0 and taking V over V0, where V and V0 are the voltages that we've just read off these 2 devices. And then what I can do is I can switch to AC power, and I can do the same thing. So when I switch to AC power, now instead of the ratio of resistances, it's going to be the ratio of impedance to the resistance in the resistor box. And so the formula looks a little different, but what it's telling me is, what I can do now with this is I can come up with a value for the resistance in the solenoid, and I can come up with a value for the impedance in the solenoid. Once I have resistance for this device, and once I have impedance determined, what I can do is I can use that to work back and come up with the reactance. So I can solve for the reactance from here, and then from this equation I can solve for the inductance. So I can solve for the inductance or the self-inductance of the inductors using this series of formulas. So I'm going to have a data table. I'm going to take a series of measurements at DC. So these are my DC measurements. And then this is my AC measurements. Let me go ahead and write that down. So these measurements, I'm using a DC power supply. And then here I'm using an AC power supply. All right, and so for the DC power supply, I'm getting a series of resistances. For the AC power supply, I'm getting a series of impedances. And I can average those. So I'm going to average those. I'm going to first of all check and see if these numbers match up. They should. When I change the resistor box, what's going to happen is the voltages measured between the devices, those are going to change. But when I calculate how much resistance is in the device or how much impedance is in the device, I should get the very same numbers. Or not the very same numbers, I should get something that's very similar, all right, when we're doing that. So that's the idea here. Let me plug this back together. All right, so we're going to get R's from here, we're going to get Z's from here, and then we're going to plug into these equations to get, first of all, reactance, and then get inductance. Now, there's a theoretical comparison we can make. There's a formula that we've been using for solenoids. Now, the formula we've been using for solenoids is a bit of an approximation, and it's assuming that the solenoid is really long compared with the radius or with the diameter. Now, this solenoid, you know, that matches up with that requirement pretty well, but there's a second solenoid we want to measure. We want to come back and repeat the measurements with the large solenoid. And when we do that, what's going to happen is the theoretical values for this one, I'm guessing, are not going to be as reliable. This one is not really very long compared with what the diameter is. So unfortunately, we're kind of left with that. Now, well, let's connect this and see. So I'm going to connect this. Now, one of the issues I'm going to run into problems with here is when I connect this. If I put this resistor box at 1 or 2 or 3 ohms, the voltage is all going to get shifted over here. There's 5 volts to work with, and the resistance will get shifted over here because that's where all the resistance is. So what I got to do is this. With that smaller solenoid, having, you know, 1 or 2 or 5 or even 10 ohms was fine. But now that I got this big one, I'm going to have to go up and maybe use 50 or 60 or 70. And when I switch over to AC, how much impedance will this have? And this is going to have a lot more impedance. The impedance is going to be much, much larger because it's got so many loops, right? And so it's going to have a much higher inductance, and that's going to contribute to what the impedance is. So I've got to plan for that with my resistor box. So, you know, the resistor box, maybe it has to get set to 400, 500, 600, 800 in order to do the measurements for the much larger solenoid. All right. And then, as I was saying, there's a theoretical formula for this. Now, I got the ruler out. Here's a ruler. I measured the lengths and the diameters and divided by 2 to get a radius. And I was conservative. I measured the inner diameters and wrote all those numbers down. Now, those can be plugged in to get a theoretical estimate as to what the values are. Our method here is actually pretty reliable. The resistor boxes are pretty reliable. The voltmeters are very reliable. And so we're hoping we're going to do much better than the theoretical value. The theoretical value is just going to be an estimate, and the values we end up with should be very good. Now watch. One thing you want to watch for is watch for the resistance measurements. These should be very similar. If they're not, go back and check. And then again, the impedance values, the 4 values we have here, we're going to do 4 runs for each of these. those should match up pretty well also. So if they're not matching up, stop by and let's take a look at your numbers and see what's happening. But this actually should be a pretty reliable lab. Again, I'm expecting that the measured values that we come up with are going to be more reliable than the theoretical estimates that the formula is giving to us. These just don't match the geometry of that the theoretical formula was based on. So let's take a closer look too. Let me grab a camera here and go in a little closer and see what we can do on this lab. So once again, here is our power supply. Right now I've got it, it's turned off. Right now I'm using the 5 volt, this is 3 amp. I got to get to the 5 volt, 0 to 5 volt DC, and then I turn this all the way up. Now, if you notice, because we're using this ratio method with the resistances, we actually don't need to know that. We don't need to know what the voltage output of the power supply is. So that's kind of handy that we don't have to have details on that. And then here's the 6.3 volt AC that we've worked with. I think we've worked with that before. Here's maybe the new item is this resistor box. And you know, right now I have it set up with 4 ohms. Well, let me see. I'm going to turn this back down to, since we're working with the large inductor, I think I better turn that up. Maybe I'll turn it up to 400 ohms. That's going to be a lot more ohms. But anyway, there is the large inductor. There's the circuit that we're working with. And then here's the voltmeter with just those simple contacts. All right, that's the setup. Let me know if you guys have any questions. Stop by and we'll get whatever questions you guys have. We'll get those answered right away.